Welcome back to the Deep Dive. Today, we're powering up, but maybe in a slightly different way. We're diving into the heart of what moves so much of our world.
Electric motors.
Exactly. Specifically, we're looking at this like unsung hero that spins constantly, billions of times a day, probably without us even thinking about it, the induction motor.
Right.
And, we heard you. You asked for an explanation that really cuts through the jargon, makes these complex ideas clear, especially if you're just starting out.
And that's a great goal.
So that's what we're aiming for today. Did you realize that these induction motors, even though the basic idea is old, they're still the most common, most robust workhorses out there?
It's true.
Mostly because of this really clever trick with magnetism and, get this, no physical contact involved in the key part. That's the kind of thing we want to explore. Our mission. Unpack the principles, the structure of these motors. Why are they so common? Think washing machines, factory conveyors. We want to demystify these powerhouses. Okay, let's get into it.
Absolutely. And what's really, fascinating is how this fundamental, almost elegant principle of electricity and magnetism comes together. It creates motion so efficiently, so reliably.
Yeah.
They're just everywhere, quietly doing their job. But yeah, the inner workings can seem a bit mysterious.
Totally.
So hopefully we can make that mystery understandable. Because getting these basics really does demystify a lot of the tech we use every day.
Okay, so let's kick things off simply for that beginner level.
All right.
A really key distinction first. When we think small motors, like maybe in a kid's toy or a simple handheld tool,
Right.
a lot of those use direct current, DC. But step into your kitchen, your laundry room, or definitely any industrial place.
Oh.
The really powerful motors, the vast majority, they run on alternating current, AC.
That's the standard for grid power, yeah.
And the star of our show today, these super common AC motors, they're mostly induction motors.
That's the one?
No, just high level. How are they different from those DC ones? You mentioned DC relies on like a fixed magnet and another magnet on the spinning part, the armature, pushing each other.
Generally speaking, yes. In many DC motors, you have an armature, which is an electromagnet, spinning inside a magnetic field created by stationary magnets. The interaction, the push and pull between those fields creates the rotation.
Okay.
But induction motors, they have a different approach. Maybe, like you said, a more elegant dance.
Right. So what's the core difference there?
Well, the key concept for induction motors isn't that direct magnetic push onto an energized rotor from outside. Instead, it's about creating a rotating magnetic field in the stationary part, the stator.
Okay, a rotating field is the part that doesn't move.
Exactly.
Right.
And the spinning part, the rotor, it simply follows that rotating field.
Follows it.
Yeah, it's induced to follow it. This following without direct physical electrical contact, that's not just a minor design choice. It was a huge leap forward. It dramatically improved reliability and lifespan, especially compared to earlier motors that needed brushes and things. That's why, some really old, reliable machines still humming away probably have an induction motor inside.
That following idea is interesting. How does something invisible, this rotating field, actually make the rotor spin without, physically pushing it? Can you walk us through that step by step?
Sure. So imagine the stationary part. It's got windings, and we're feeding it AC power to create this invisible magnetic field that's constantly moving, rotating around.
Okay, got it.
Now, you place the rotor inside that field because the field is moving relative to the rotor conductors. A principle called electromagnetic induction kicks in. It's like a transformer, basically.
Oh.
This moving magnetic field induces an electromotive force, an EMF, or voltage, in the rotor's conductors.
Right, induction.
And that induced EMS causes an electric current to start flowing within the rotor itself.
Okay, so now the rotor has its own current flowing through it, even though it's not directly wired up.
Precisely. And here's the next step. Whenever you have current flowing through a conductor, especially within a magnetic field, that conductor creates its own magnetic force.
Ah, so you've got the stator's rotating field.
Yeah.
And now the rotor has generated its own magnetic field because of the induced current.
Exactly. So now you have two magnetic fields interacting, the original rotating one from the stator and this new one created by the rotor current.
And that's what makes it spin, the interaction.
That's what produces the torque, the rotational force. Think of it maybe like dangling a metal object near a spinning magnet. The object will start to spin too, right? Trying to keep up.
Yeah, I can picture that.
It's a similar idea, but much more controlled and powerful in a motor. The rotor is constantly chasing the stator's rotating field, but because of the way induction works, it never quite catches up to the exact speed of the field. There's always a slight difference called slip, which is actually necessary for the induction to keep happening.
Wow, okay. That's that's pretty ingenious. But it does sound maybe a little more complex than just having magnets push each other like in a simple DC motor.
Conceptually, perhaps.
So why? Why are these induction motors so preferred, especially in industry? If the principle seems a bit indirect, what makes this indirect interaction so powerful and reliable?
Yeah, excellent question. And it really gets to the heart of why they're everywhere. The answer really boils down to two main things. They have an incredibly simple and robust structure.
Simple and robust. How?
Okay, think back to those DC motors we mentioned. They often need physical contact points, things called commutators and brushes.
Right, you mentioned those.
These are needed to get the electricity into the rotating part, the armature. But these parts are constantly rubbing together as the motor spins.
Really, as they wear out.
Exactly. They wear down, they can create sparks, electrical noise. They need regular maintenance, replacing the brushes. That adds cost and potential downtime.
Okay, I see where this is going. So the induction motor avoids that.
Precisely. Because the rotor in an induction motor works purely by those induced currents we talked about.
Yeah?
It doesn't need any physical electrical connection to the outside circuit while it's running.
No brushes, no commutators.
None on the rotor side for the power transfer, no parts constantly rubbing to deliver the main power. The implications are huge.
Like what?
Well, dramatically lower operating costs because there's less maintenance. Much higher reliability because those key wear parts just aren't there. Less electrical noise, too.
Okay, that makes a lot of sense for, say, a factory.
Absolutely. That inherent simplicity and robustness are why they totally dominate in demanding industrial settings where you need something to just run and run and run without fuss. Downtime is expensive.
Right. So let's connect that to what we actually see. You find these everywhere. In our homes, you mentioned washing machines, fans.
Those are typically single-phase induction motors. They're designed to run perfectly well on the standard single-phase AC power that comes into our houses. So yeah, fans, air conditioners, fridge compressors, washing machines, lots of common appliances.
Okay, single phase for homes.
And then when you need more power, more oomph, you step up to three-phase induction motors.
Three phase. That sounds more industrial.
It is. These are the real heavy lifters. The workhorses you find in factories, large buildings, driving big machinery. Think conveyor belts, large pumps, industrial fans, machine tools.
Why three phase for those? What's the advantage?
Well, fundamentally, using three-phase power makes it much, much easier and more efficient to create that smooth, continuously rotating magnetic field in the stator that we talked about.
Ah, the magic rotating field.
Exactly. With three phases, you get a more constant power delivery and a more naturally rotating field compared to single phase, which needs some extra tricks to get started and run smoothly. So three-phase motors generally offer smoother operation and can deliver more power for their size.
Okay, so that distinction explains why we see different types in different places, home versus factory.
Pretty much. It's about matching the motor type to the power available and the job it needs to do.
So let's dig into that three-phase rotating field then,
Eh.
because you said that's the key, the secret sauce. How is it actually generated? How do you make a magnetic field rotate without moving parts in the stator?
Right, it's clever. It comes down to how the stator is wound. Imagine the stator, that stationary outer part. It has coils of wire, the windings, arranged in slots.
Okay.
For a three-phase motor, these coils are arranged physically around the stator, spaced out typically at 120-degree intervals from each other. So you have three sets of windings positioned symmetrically.
120 degrees apart, like points on a triangle, sort of.
Exactly. And here's a neat detail. Coils that are directly opposite each other across the stator's diameter. They're often wound in opposite directions.
Opposite directions, why is that?
It helps ensure that as the current changes in the three phases, the magnetic fields they produce combine constructively to create a rotating effect rather than just pulsing in one place or canceling each other out. It's part of the design to get that smooth rotation.
Okay, so you've got these coils, 120 degrees apart, some wound opposite. Then you apply the three-phase AC power. What happens?
Well, three-phase AC power means you have three separate currents, each peaking at a different time, one after the other, smoothly rising and falling.
Right, they're out of sync.
They're out of phase by 120 degrees, matching the physical spacing of the coils. So as these three currents flow through their respective windings, the strength and polarity, north or south, of the magnetic field produced by each winding is constantly changing.
Okay.
Because the currents peak sequentially in the windings arranged around the circle, the overall magnetic field that results from combining the fields from all three windings effectively rotates around the stator.
Ah, so it's not physically moving, but the peak of the magnetic field is moving around.
Precisely. If you could visualize the magnetic flux lines, you'd see the strongest point, say the North Pole, smoothly sweeping around the inside of the stator. It looks and acts like a physical magnet rotating inside, even though the stator itself is completely still.
That's the rotating magnetic field.
That's it. We call it hajanjagi in technical terms. It's this elegant electrical solution to create rotation without needing mechanical complexity like brushes on the rotor.
Okay, that makes sense. So bringing it back to the physical machine, what does one actually look like inside? You've got the stator making this field and the rotor following it.
Right. So any typical induction motor, especially a three-phase one, has those two main parts you mentioned. The stator, which stays put, gets the electrical power and creates the rotating field. And the rotor, the part inside that actually spins and does the work.
And the rotor connects to the outside world.
Yeah, the rotor has a shaft attached to it. That shaft sticks out of the motor housing, and that's where you connect your load, maybe a gear, a pulley for a belt, a pump impeller, whatever needs turning. The stator gets the electricity, the rotor delivers the mechanical power.
Got it. Can we look a bit closer at the parts? You mentioned squirrel cage motors earlier.
Yes, that's probably the most common type of induction motor rotor. Let's break down the structure, using that as an example.
Okay.
First, the stator. It generally has three main bits. One is the frame. That's the outer casing, usually made of cast iron or sometimes aluminum. Often, like you might have seen, it has ridges or fins on the outside.
Yeah, the bumpy bits, what are they for?
Cooling. They increase the surface area to help dissipate the heat that the motor naturally generates, keeps it running efficiently.
Makes sense.
Second, inside the frame is the stator core. This is crucial. It's not a solid chunk of metal. It's made from many, many thin sheets, laminations of silicon steel, maybe only 0.35 millimeters thick, stacked together.
Thin sheets, why not solid?
That's to reduce energy losses. A solid core would have strong eddy currents induced in it by the changing magnetic field, which basically just wastes energy as heat. Using thin insulated laminations breaks up the paths for these currents and makes the motor much more efficient.
Clever.
And this laminated core has slots running along its inner circumference.
And that's where the wires go.
Exactly. That's the third part. The stator windings. These are the carefully wound coils of insulated copper wire placed into those slots in the core. These windings are connected to the external three-phase power supply.
Okay, so frame, core, windings for the stator. What about the rotor, the squirrel cage part?
Right. The rotor in a squirrel cage motor is beautifully simple, which is key to its robustness. It also has a laminated core, typically cylindrical, also with slots.
Similar core to the stator, then.
Similar in using laminations, yes, for the same reasons, reducing eddy currents. But here's the defining part. Instead of insulated wire windings, molten aluminum is usually poured or cast directly into the rotor slots. These form solid bars of conductor material.
Aluminum bars.
Yep. And crucially, at both ends of the rotor core, these aluminum bars are all connected together by solid conducting rings, often made of copper or aluminum alloy. These are called shorting rings or end rings.
So the bars run along the rotor and the rings connect all the ends together.
Exactly. If you were to magically remove the iron core, you'd be left with a structure of bars connected by end rings that looks very much like, well, a cage for a squirrel or hamster.
Okay, I see it now. The squirrel cage.
That's the name. And it raises that question you touched on earlier. Why this design? What makes this simple cage so effective?
Yeah, why is that the go-to design? It seems almost too simple.
Well, that simplicity is its strength. Think about it. You've got solid bars permanently connected by end rings. There are no wire windings to potentially break, no insulation that needs to be carefully managed inside the rotor slots, no external connections needed at all for the rotor circuit.
Right, because the current is induced.
Exactly. The current is induced directly into those solid, robust bars. It flows through the bars and completes the circuit through those sturdy end rings. It creates its own magnetic field, interacts with the stator's field, and produces torque.
So it's just incredibly durable.
Incredibly durable, virtually maintenance-free from an electrical perspective on the rotor side. It can handle heat, vibration, harsh industrial environments, much better than a rotor with delicate wire windings and connections would. It's a masterpiece of efficient, robust, cost-effective engineering. That's why it's so dominant.
Wow. Okay, that really paints a clear picture.
Mm.
What a journey we've taken, huh? From just separating AC and DC motors
Mm-hmm.
to understanding this cool idea of induced currents and rotating magnetic fields, and these invisible forces doing all the work.
Yeah.
And then finally seeing how that translates into the actual physical parts, like that tough squirrel cage rotor. Hopefully for everyone listening, especially if you are new to this, you've got a much clearer idea now of these silent workhorses
They really are.
powering so much around us. It's amazing how something based on such fundamental physics can be so reliable and cost-effective in the real world.
It truly is an elegant piece of design, isn't it? Just how electricity and magnetism are harnessed to create motion without needing that direct physical contact, leading to such robustness. It's clever engineering.
Definitely.
So maybe next time you hear that low hum from your fridge or you see a big machine moving smoothly in a factory, perhaps you'll, picture those invisible rotating magnetic fields inside silently spinning the rotor.
Yeah, a little appreciation for the physics at work.
Exactly. And maybe a final thought to leave you with. Considering how fundamental this principle of induced current and contactless motion is, how might we see this evolve? How might it influence the next generation of motors? Maybe even quieter, even more efficient designs in the future. Something to think about.
A great thought to end on. Thanks for walking us through all that.
My pleasure. Thanks for having me.